So again, page 51, we got Lewis dot structures for compounds is what we're going to be doing. You see that we've got two objectives here. First objective is draw visual representations of bonds based on chemical formulas. And then second objective, identify visual representations of bonds based on chemical formulas. So those are our two objectives we have to tackle here. And what I want to point out for you guys is we've got the visual representations that we're doing in both of those objectives are going to be the Lewis dot structures. So both of those visual representations for bonds we're going to show in Lewis dot structures. Okay. The other piece I want you to see is that we need to be able to draw them for this first objective. So we'll need to be able to draw Lewis dot structures as long as I give you a formula. And you also need to be able to identify which is the correct Lewis dot structure if I give you a formula. Okay, so I need to either be able to show you a list of Lewis dot structures and you show me which one is the correct one, or you need to be able to draw that out yourself. Okay, so those are our objectives. Some definitions real quick. We've got a single bond is going to be a bond when you have only a single pair of electrons shared. Okay, so a single bond is you've got one pair of electrons shared. If it's a pair of electrons, then that means one pair of electrons would be how many total electrons? So that's how you're thinking through that single bond. Okay, then you've got double bond, which is the same thing except you've got two pairs of electrons bonding together. And then a triple bond is a bond between two atoms that have three pairs of electrons shared between them. Why would we use a Lewis dot structure? It's simple enough, but why would we use it? So it helps us to be able to see how a molecule is going to actually organize itself, like the order that it's going to go in. Why that might be helpful is when things freeze, they usually get smaller, okay? If you freeze a liquid, usually that liquid gets smaller in size. Do you guys know what happens whenever you freeze water? It actually expands. The only reason that we can explain that is because we know the structure of what a water molecule looks like. We explain that using Lewis dot structures. Okay? So that's the cool thing with this is we get to go through and actually explain some really cool situations like why does water expand? Okay? So then molecular formula is what tells us how many atoms are in a single molecule of the compound. So if we're looking at this O2, how many oxygens are in that O2 molecule? 2. What you are seeing is that number down underneath the element. Okay? Do you guys know what the prefix for under or below is? Do you know what the prefix for under or below is? Sub. Like, for example, the thing kind of like a boat that goes underwater, what's that called? A submarine, because it is below the water. So sub is the prefix that means below. So the number that is below the element is called a subscript. Because the number that goes below that element, it tells us how many of that element are there. Okay? Subscript. Yes. Bless you. You are welcome. Then, if we're looking at that next one, CO2, does carbon have a subscript shown? No. It doesn't. What do you think we can assume that's going to end up being? Right, so how many carbons there?
1.
class, how many carbons are there in CO2? Awesome. How many oxygens? What do we call that number on bottom? Subscript. You guys got it. So that goes through, again, you've got sucrose here, has 12 carbons, 22 hydrogens, and 11 oxygens. You guys have a good lunch. So we've got place each element's Lewis structure, then you go on to pair up single electrons for a single bond, and then once you do any leftover single electrons, usually that's going to be good, and so that's why after that you check to see, you check the central and outside elements to see if they have their octet. Okay? If they've got their octet, then everything's golden. Now, hydrogen, because hydrogen is an exception, it's only going to have 2. So if it has 2 electrons around it, then it is good and it's happy. Okay? Anything else needs 8 valence electrons. So in order to start out, we have to know what the middle one is going to be. You guys don't have to write this. This is just for you to know which ones are in the middle. There are 3 main ways for you to know which ones are in the middle. First is usually either the element that only has 1 or the first element in the chemical compound is going to be the middle element. Okay? The only exception, again, because hydrogen isn't ever going to be the middle one, even though sometimes it'll be the first element on your formula. Okay? So like for water, you've got H2O. Which one only has one of the element? So that's going to end up being your middle element. Okay? If you can't figure it out based on those 2, then the next thing you would check is whichever one is closest to the carbon group. Okay, so closest to having 4 valence electrons. So let's do the water H2O's Lewis dot structure. First, we got to put the Lewis dot structure for each element. So oxygen is going to be the one in the middle. We need to find how many valence electrons for oxygen. It does have 6, so we've got 1, 2, 3, 4. Then I start pairing it up. 5, 6. Then how many hydrogens do I have here, Will?
2.
I end up having 2, yes, sir. So I'm going to put hydrogen. How many valence electrons for hydrogen?
1.
Awesome. Put that. Just so you guys are kind of seeing the way that I'm organizing and why I'm organizing it that way, you're going to end up pairing up the single electrons, right? So I'm trying to structure it to where I know I've got a single electron here, a single electron here. Go ahead and put those close to each other, okay? That's just how I'm structuring it so that it's a little bit easier as I'm starting to work through it. I've got a second one I need to place, so hydrogen, another single electron. Then I start pairing up the first set of single electrons. So those 2 electrons are going to get shared so that it'll cause a single bond here.
Does it have to be below it?
No. And then these 2 also are going to get shared to give a single bond there. Okay. And then at this point, I don't have any other single electrons, so I need to check, do I have the octet? So I'm looking here. I've got 1 lone pair, 2 lone pair, so that's a total of 4 electrons there. And then 1 shared pair of electrons and a second shared pair of electrons. That's another 4 electrons around it. So 2, 4, 6, 8 gives me my octet. So is oxygen happy? Booyah. So I'm good with that. Then I got to check hydrogen. around that hydrogen, it's got one shared pair of electrons. Does hydrogen want only two? Yeah, it was our exception. So it's happy there. Then hydrogen over here, same thing. It's got one set of shared electrons. Okay, so that would be my final answer here. Then NF3. Let's look at NF3. Which one do we think is going to go in the center here? Exactly, the N, the nitrogen. So we're going to put nitrogen. How many valence electrons, Lauren? Awesome. 1, 2, 3, 4, 5. Then fluorine. How many fluorines do I have, Everett? 7 valence electrons. How many fluorines?
How many?
Yes.
Oh, 3.
Right, because my subscript is 3 for the fluorine. So you said we had 7 valence electrons, so we'll go ahead and get that. 1, 2, 3, 4, 5, 5, 6, 7. Bless you. 1, 2, 3, 4, 5, 6, 7. Okay. And pair up my single electron, so that's there, there, and there. So single bond, single bond, single bond. Any other single electrons? Super cool. So I'm going to check. I've got 2, 4, 6, 8 electrons around my nitrogen. So that one's good. Fluorine has 2, 4, 6 in their lone pairs. 7, 8 also has its octet. Okay. What questions do you guys have on this? All right, you guys go ahead and try CCl4. Ask me any questions you guys have, and we'll check that in a second. The middle element is going to be what, Riley?
Me?
Mm-hmm.
Oh, carbon.
Mm-hmm. Carbon. And for carbon, how many valence electrons, Olivia?
For carbon?
Mhm.
4.
Awesome. 1, 2, 3, 4. And then around that, what am I going to put? Jason?
The CLs.
Exactly. How many?
4.
Awesome. So I'm going to structure that around the Cl there. How many valence electrons for Cl? Jada?
7.
Awesome. So I've got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Then what am I going to do next? What am I going to do next? TJ? Hmm? The octet, and how am I going to do that?
By connecting 2 bonds that are closer to the middle.
Exactly. So I've got bond there, the 2 electrons here, the 2 electrons here, and the 2 electrons here. Okay? I don't have any other leftover electrons that are single, so I'm going to check to make sure that my octet is full. I've got 2, 4, 6, 8. So that's carbon's octet, and 2, 4, 6, 8 for chlorine's octet. Okay, so we are good. Work through a couple more. SiOF2. SiOF2. What do you guys think the middle element is going to be here? So we think maybe oxygen? Okay. So remember the first element typically is, and if you can't tell, like for here, we've got one Si and one SO. I'm sorry, one O. So check to see which one's closer to the carbon group. All right. So Si is going to be the middle one.
And where are you gonna put O2?
So it'll become more clear whenever we get to that step. How many valence electrons for Si? 1, 2, 3, 4. Then now I need O and F2. So I'm just going to, right now is just like a rough draft phase. So I'm going to put O right here and see how this works. That has 6 valence electrons. 1, 2, 3, 4, 5, 6. Notice I'm keeping my single electrons off over close to the Si because that'll be where they end up going anyways. And then how many Fs do I have? So I've got F and F. Each of those have 7. Could I have put the other F on the top? Yes, definitely. This is just rough draft at this point. 1, 2, 3, 4, 5, 6, 7. Okay. Start pairing up the single electrons. So I've got single electron there, single electron there, single set of electrons there. Okay. Then double check to see if I have octet. This is Si has 2, 4, 6 in its shared electrons. So it only has 7. Does it have its octet yet? So it is definitely not what it wants to be. So then what you should see here is that I have 2 sets of single electrons right there. So those are going to actually come into this bond right here. And instead of a single bond, that's going to make a double bond. Okay? So again, I'm showing you guys that's like kind of the rough draft so you can see how that goes. And then here's what that'll end up final look like. So Si with a double bond to oxygen, single bond to F with 3 lone pairs around it, single bond with F, 3 lone pairs around it.
Will you know what you just wrote so I could-
Yes, I will. Thank you. So that would be like the final draft. Okay. Questions before I move on? Okay. Then N2. For N2, am I going to have a center atom here? No, I only have 2 atoms, so we're just going to put them next to each other. N and N. How many valence electrons for N? Zachariah? Super cool. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We definitely know what are we going to do first, Landon?
I'll connect them
Right, which, like where?
on the left and right side.
Right, exactly. So we've got a single bond there for sure. Okay. Neither of them have an octet, so they're going to keep trying to move electrons around until they get an octet. What else could they do to continue getting closer to their octet? Justin? I'm sorry, Jason?
The 2 at the top and the 2 at the bottom should connect.
Exactly. So we'll have that come in to get a double bond, and the top or the bottom ones will come in and get a triple bond. So we'll have N with a lone pair, with a lone pair, triple bonded to N with a lone pair. So SiS2. What's going to go in the center for SiS2? Awesome. It is Si. We've got 1, 2, 3, 4. S. How many valence electrons for S? 1, 2, 3, 4, 5, 6. S also has 6. I'm going to bond these two together. Bond these two together. Then I've got these two electrons are going to come in to form this bond right here. So there'll be a double bond in this section between S and Si. And then these electrons are going to also come in and form a double bond. So I'll end up with Si double bonded to S with 2 lone pairs, double bonded to S with 2 lone pairs.
Are we gonna practice this? Or
Yes, we are.
Okay. 'Cause I'm beyond tired.
Now that I've done that one, did the double bonds make more sense? Okay, cool. So then you guys, again, will need to be able to draw Lewis dot structures for simple molecules like what we've just done, or simple ions. I'm going to do actually one extra bonus example, just because I noticed in first and second block that this was a question that got asked a lot. Okay? So let's look at pH4 with a +1 charge. Okay? pH4 with a +1 charge. We've got phosphorus is going to go in the middle. It's got 5 valence electrons. 1, 2, 3, 4, 5. I've got 4 hydrogens, so hydrogen, 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 hydrogen. Because I've got a +1 charge, what happened to the number of electrons? So I've got 1 fewer electron for one of these hydrogens. Okay? So just for convenience, I'm going to pick that one that no longer has an electron. Okay? And then 1, 1, 1. Okay? So I've got bond here, bond there, bond there. So at this point, we've got, check this, phosphorus has 2, 4, 6, 8. Does phosphorus have the octet at once? Cool. These hydrogens have what they want because they've got 2. What about that hydrogen? It's got no electrons, so it isn't actually happy. What's going to happen is this phosphorus right here is going to be very kind and offer to share those 2 electrons in its lone pair. So that'll actually come in and make a bond with that hydrogen. So that'll end up looking like phosphorus bonded with all of its hydrogens and then bonded with an extra hydrogen. No lone pairs. That's that last step where I say rearrange to make sure that they get an octet. That's the situation here. And then if you wanted to specify that it had a +1 charge, you would do that.
Is that single bond?
Single bond, yes. Because you're only having 2 electrons bond between them. Yep. All right. go ahead and try the practice. That is worksheet 5 in your unit 7 work.